You should have now completed the reading assignment from chapter 3 of the textbook about torque and moments. And they do a good job of differentiating between these two quantities. Torque, which tends to be associated with rotations. So the tendency of a force to make something rotate. In physics, we always call this torque. But moment is often interchangeably used with the word torque. They have the same units, they have the same equation, but this tends to be, so in physics, we always do this, in like first year physics courses. The moment tends to be associated with bending of something. And so if you want like a diving board to bend, you would apply a force. That force produces a torque, but the torque results in bending. And so this word moment, this often engineers will use moment more than they'll use the word torque. So I'll mainly use the word torque because we're going to be interested in rotations. We're not going to be interested in bending or breaking things. So the equation that you have written down from the textbook is M. So this is moment. The units for that quantity are newtons times meters. So you just say Newton meters. And then this is the force in newtons. Now, unfortunately, this quantity D, it has all kinds of symbols. It could be called D perpendicular, it could be called L, could just be called D, but this quantity D, which I like to put D perpendicular to really stress the idea that this is a perpendicular distance to lines of action. But sometimes it's called L as well. But in any case, it's the lever arm, or sometimes called the moment arm. And it would be in meters. Now, it doesn't have to be in meters. You could, if you put it in millimeters, you would just then say the torque is equal to a Newton millimeter. And so the symbol for torque that we use in physics that you may see in other textbooks, or if you go online looking for things, this is a common equation that you'll see. So this symbol tau, that's the Greek letter tau, that's what we use for torque. And then, like I say, this lever arm, we usually use D perpendicular in physics. Okay, so what does this quantity torque have to do with? The idea of it being a vector is not going to be of concern to us here. It is actually a vector that points perpendicular to the plane in which things are rotating. So if you consider a teeter-totter here, this fulcrum or the pivot point, so sometimes it's called the pivot point, sometimes it's called the fulcrum, or what I like to use is the axis of rotation. And the definition of that is if you were to put a line perpendicular to the page through that point, and you let the teeter and totter, that line doesn't move. Whereas if you were to put a line through one end of this teeter-totter and let it teeter and totter, that line would be going up and down with the teeter-totter. So that can't be the axis of rotation. So we're going to, and then what they often say in engineering is we take torques about this point. In other words, all lever arms are referenced to that point. You have to go back to that point. So let's just say we have two children sitting on this teeter-totter, exerting forces of gravity, but maybe they're just toys, so they're really small. So F1 will be 10 newtons. And then we're going to put a heavier child over here, or heavier toy, twice the mass, twice the weight. And we're going to be interested in how this teeter-totter balances. So most of the questions we're going to be dealing with, we're going to be in balance. And the pivot point or the axis of rotation is always going to go through a joint. The forces are going to be from the weight of your arms or legs or head, as well as any weight that you may be holding, say in your arm or something. And then we're going to be interested in what are the muscle forces that are required to hold your body in that position. So, but just to illustrate what a torque is here, we measure the distance from this pivot point over to the line of action of the force. Now remember what line of action is? It's just this imaginary line that goes right through the force. Make it as long as you need to. It doesn't matter. And it doesn't matter where on that line this F1 is applied. The torque due to that force has to do with how far away the line is from this axis of rotation. So that would be D1. That would be the lever arm for force 1. And let's say that we're told this is 2 meters. Now over here, the line of action for F2 is this line we draw here. And then D2 is measured from O over to D2. Okay, so we want to calculate the torques due to these two forces. Now, we will have to worry about whether these forces are trying to get this teeter-totter to rotate clockwise or counterclockwise. And that's how we're going to classify torques. So this F1, if you put your finger on O and imagine letting the teeter-totter go as a result of F1, it's going to go clockwise. So this is a clockwise torque. So we usually just say CW. But over here, if you look at F2 and put your finger on O and then just let F2 make this teeter-totter rotate, it's going to try to go counterclockwise. So this one produces a counterclockwise torque. And so it's CW. Now, conventionally, we do counterclockwise as positive in physics and clockwise as negative. Your textbook's a little wishy-washy on that. And they sort of just decide, well, let's just make clockwise positive or see what the net is in relation to what we've guessed. But we don't have to worry about positive and negative. We simply have to balance them. And so the torque from F1 would be D1 F1. And then the torque from F2 would be D2 F2. And I'll just go absolute value. Don't worry about positives and negatives. But we're going to balance. So we're going to say clockwise equals counterclockwise. And so the D1 F1 would have to equal D2 F2. And the question may be, well, just what is D2? How far away do we put that 20 Newton force to get this teeter-totter to balance? And so we could just solve for D2. And that would be D1 F1 divided by F2. So it would be 2 meters times 10 newtons divided by 20 newtons. And we would see that it has to be at only 1 meter. So if you have twice the force up here, you put it half the distance away from the axis of rotation, and you're going to get the same torque as if you have a smaller force a distance 2 meters. So you can see how important distance is here. You can't just say a big force produces a big torque. It doesn't necessarily. It all depends on how far away the force is, and it also depends on the direction of the force. If you had a teeter-totter and you pushed on the end like this with a force of 10 newtons, even though at this point of application out here, this force may be 2 meters away, well, what's the lever arm for this force? It turns out to be 0. The line of action of this force is like this. Now, there is no perpendicular distance from O to the line of action because the line of action goes through O. Okay, so this is a very important point. There's no torque from a force if line of action goes through axis of rotation. So any force, any joint force that like from bone on bone that goes through the joint, it doesn't produce any torque. You have to move away from the joint with a force in order to produce torque about that joint. Okay, so this torque would be 0. Oh, torque equals 0. Okay, so I want to do the examples that are in your textbook, which are really good examples, and they're very well laid out. I'll just go through them, and then you should also have all read them. So from your text, example 3.1, which was on page 43. It was just somebody standing on a diving board. Okay, so let's just go through that example. So you have a picture and you have the diving board and you have the person standing on the end of the diving board. What you really want to do is reduce it to a free body diagram where you just have the diving board. Now it says about the end of the diving board. So this is our axis of rotation, O, the end of the diving board here. And the person standing on the end has a weight. So that is a force due to the force of gravity of that person. And that person has a weight such that it's 882. And in their diagram, they draw the weight up here. I'm not sure why. It doesn't matter. Remember, it's the line of action that counts. You can put that force anywhere you want on this line of action. And it tells you how far away this is. This is already a perpendicular distance. So that's D1, which is 4 meters. And then you have the weight of the board itself, which seems awfully big. Whoops. W2, 1176 newtons. And it tells you the point to the center of gravity. Now, we haven't done a lot on center of gravity yet, but center of gravity will be the geometric center of an object if it's a uniformly distributed mass object. Okay, and D2, the distance out to here is 2 meters. And the question is, what is the net torque? Now, after I do my diagram, then I go and say, okay, is this clockwise or counterclockwise? W1 is clockwise, trying to get it to go clockwise. Doesn't matter whether it goes or not, it's trying to. W2 is also clockwise. So these two torques, whether they're positive or negative, doesn't matter. We're going to add them up, and the answer is going to be a total clockwise torque. And so your textbook calls it M net. Oh, I think your textbook calls it M0. This means about the point 0. But usually I'm going to call it the axis of rotation. And then what I'll say is put the axis of rotation in the elbow joint or the knee joint or the hip joint. And that's your O. Okay, so it's just equal to the force is the same. Oh, they call this the force. This is a force. It's the force of gravity due to the person. And so we just have D1 W1 plus D2 W2. So we simply have to, now once again, I'm going to call this torque, and in my solutions I've already done from last year, it's going to be, the symbol is going to be torque. So we just multiply these things together. 4 meters times 882 newtons plus 2 meters times 1176 newtons, and you get a net clockwise torque of 5880 Newton meters. And then you would say clockwise, and that's your net torque. Okay, so that was pretty easy. The next example, 3.2, is the one where the person has you're doing quadricep extensions on one of those machines at the gym. This is example 3.2, quadricep extensions. Now, the point of this example is that you'll see that depending on the position of your leg, this is your foot, and you've got this weight, you hook your foot around the weight. Depending on the position, whether your leg is straight out, here's your knee, and your quad, of course, has to pull to keep your foot out like that, or whether your leg is straight down or something in between. The force in your quadricep in order to maintain your foot in that position is not linear, it's drastically different. And it requires this requires by far the biggest force in your quadricep muscle to keep your foot in that position. Turns out this, when you're at 90 degrees here, the weight hanging on your foot, there's no torque at all due to that one. Okay, so let's see how you do this when you change this range of motion. Okay, we'll do first the diagram where the leg is just straight out. This is exactly like the diving board. So position 1, remember you're looking at the diagram, or have looked at the diagram. Position 1 is just when the foot is straight out. Okay, now the axis of rotation here is your knee. And they would say that in the example, or I would say that in the example. Okay, so this is your knee joint. And this is just like that situation where you have the patellar tendon and you have the quadricep tendon. And that's why there's a terrible exercise to do in the gym, because the tension of those tendons on the patella and then the stress on that patella from the femur having to push on it is really, really horribly bad for you. So this is not a good exercise to do. You're way better off to do squats, but that's beside the point right now. So the force due to the weight in the boot, they call it a boot down here, is 100 newtons. And the distance from your knee to your foot, they call that B, where B is equal to 50 centimeters. So we'll put it into meters because they do. It's not entirely necessary, but that's okay. So that's your foot. And then you've got your lower leg, the center of mass of your lower leg, not necessarily in the center here, but they tell you where it is. So the weight of your lower leg, which your quad also has to lift up, is a distance A from your knee. So that's A, and they tell you that that distance is 20 centimeters. So it's a little bit closer to your knee than halfway down. That's of course because your calf is a little bigger there. Okay, and so that's 0.2 meters. So in position 1, it's exactly like the last example. You simply multiply these two together. So the net torque, they're both clockwise, is A times W1 plus B times W2, where D is equal to A and is equal to B because this is a perpendicular distance. So D1 equals A and D2 equals B. Okay, so if you put those numbers in, we've got all these numbers here, we're going to get 60 Newton meters. Okay, turns out that's the maximum torque you're going to get. So if you want your quads to work the most, you put your legs straight out like that. But now when you go to position 2, the perpendicular distance to the end of your foot is less because you've now brought your foot closer to your body. And so in position 2, you have to draw your lower leg down at an angle like that. Now the weight, remember, they still points toward the center of the earth. So W2 is still straight down, 100 newtons. And W1 is still also straight down at 50 newtons. And A is still along the length of your leg. There's A, and B is also along the length of your leg, your lower leg B. But these are no longer the lever arms, because remember the definition of lever arm. So here's our knee, axis of rotation. We have to go perpendicular to this line of action of these two forces. So the lever arms are not A and B anymore. The lever arms are these distances here. That would be D1, and this would be D2. And you always have to go back to O. So now the question is, what are D1 and D2? Well, we're going to have this triangle once again. And I said we're going to see these right angled triangles all over the place. Here's another one. So D1 is this distance, the perpendicular distance to the line of action. This side of the triangle is the line of action of the force. They tell you this angle theta, and this, the hypotenuse now, is A. So you do your trig, and you see that the D1 is adjacent to the angle theta, so this is a cosine. So cosine theta is adjacent over hypotenuse. And so if you solve that for D1, it's A times cosine theta. Okay, now D2 is exactly the same triangle, except it's got B for the hypotenuse. So similarly, D2 is B cosine theta. Now, when you go to do the torque, the net torque, about O, you use the D's. Remember W1 plus D2 W2. So you have A W1 times cosine theta plus B W2 times cosine theta. Now notice how we could factor out that cosine theta. I can write this as AW1 plus BW2 and then factor out cosine theta. We've already calculated that. That's when your leg was straight out. This factor cosine theta comes in because now you've lowered your leg a little bit. So you've gone from straight out, here's your knee, to down here, where this is theta. That's position 1, this is position 2. And so the answer here is just the answer for the straight out times the cosine of 30 degrees, which was position 2. And so this torque is less, 52 Newton meters. It means that the quadricep tendon now doesn't have to pull as hard to keep your foot in that position, but it only has to apply a torque. It's still a torque, and it all depends where that quadricep is attached relative to your knee joint. And it's going to have to supply 52 Newton meters of torque to keep your foot there. Now, they do this for the other positions as well. If for position 3, theta was, I think, 60 degrees, and so that gives you a torque of 30 Newton meters. Now, when theta is 90 degrees, so like I said before, if your foot's straight down like this, here, W, just 1 and W2, their lines of action go right through the axis of rotation. And so their torque is nothing. Because it's not because the forces aren't anything, and there still is obviously a force on your knee, like that's just because it has to hold up your lower leg, but there's no torque here. So the torque here is 0 because D1 equals D2 equals 0 because the line of action goes through the joint. Now they do a nice little graph of this for you, which is just the graph of cosine theta. So it looks like this, the torque as a function of the angle. And so what this shows you is if you're trying to strengthen your quadriceps, you can see how dramatically the torque falls off as you start bringing your leg closer to perpendicular to your thigh. And so the real training effect, and if you really want to work the muscle, it takes way more torque when you're up here. But of course, you still want range of motion and all that kind of thing. But you can just see it's not linear. If it were linear, it would go like this. And it would mean that, you know, as you move down, you would have a linearly decreasing torque. Well, it doesn't go like that. It goes as the cosine, drops dramatically. So once your leg is foot is almost vertically down, it's not much torque at all. Okay, so that's a good example. The next example is a very bizarre exercise. I've never seen this exercise done. I wouldn't normally do this exercise, but it is example 3.3. And it's you're lying on a bench with the barbell directly over your shoulders. It's your head. You got your feet on the ground. And it wants to know what's the torque as you lower this way. Well, if you're doing a pullover, I mean, you would lower it this way, but I've never seen anyone do the exercise where you lower it toward your hips. But anyway, it wants to know what is the torque when you move this off the vertical. Now, when it's in this vertical position, so let's do our line of action. The shoulder joint is the axis of rotation, so that's O. And when your hands are straight up over your shoulders, the weight of both what's in your hand, so that was W2. Now there's just one arm, so it's 300 divided by 2. It's 150 newtons due to the dumbbell in your hand. And then you've got the weight of your arm itself. That was W1, and that's 50 newtons. Now, remember, once again, here's this line of action of these forces right through the axis of rotation. There's no torque. So your shoulder muscles don't have to supply any kind of torque. They certainly have to stabilize. I mean, if you move just a little bit off that line, you're going to have to work to keep it there, but there's no torque here. So it's not until you swing this down towards your feet that you're going to get torque. And so this is what they want to know. So now this is O is your shoulder. At the end of your hand is the weight. You've got W2, the 150. Oops. Down. And then the weight of your arm is the W1. Now, since you've moved off the line of action, being in line with O, there's certainly torque from these. Question is, what is the torque? So we need to know from the line of action of the force, the perpendicular distance. Now you can go down here. So you're at O and you say to yourself, what's the shortest way to get to this line? Well, you go straight over here. Hit that at 90, that's D1. Or you go straight over here, hit that at 90, and that's D2. Now the distance where the center of mass of your arm is and the distance out to your hand is the same. Doesn't matter where your arm is, as long as you keep it straight. And so these distances are given to you. This one's A, this one's B, and those are fixed. Doesn't matter where your arm is. So A, they tell you, is 24 centimeters. And so this is 0.24 meters. And B is 60 centimeters. And so this is 0.6 meters. And those don't change. The thing that changes are D1 and D2 as you rotate about your shoulder. Now they're giving you different angles here. They're giving you this angle up in here, theta. Same as this one. So the triangle is different now. It looks like this. And this is what you're going to have to be able to do. You're going to have to make these triangles, figure out where the D's and A's and B's are. So B is always the hypotenuse. That's the distance along your arm. That's the length of your arm. O's down here, and this is D1. Oh, sorry, that's D2, if we're doing B. Okay, so now here's our triangle. Which is it, sine or cosine? Well, you can see D2 is opposite the angle. This is sine. So sine theta is opposite over hypotenuse. And so in this case, we use D2 is B sine theta. And it's the same triangle for D1. D1 is also A sine theta. And so now when you go to do the torque, first of all, they're both counterclockwise torques because they're trying to make your arm rotate counterclockwise. So these are both CCW, counterclockwise. So we add them together and the result's going to be counterclockwise. So M about your shoulder is D1 W1 plus D2 W2, which is going to be A W1 plus B W2, and I'm going to factor out the sine theta. Now, when your arm was directly over your shoulder, theta was 0, and sine of theta is 0. That's why the torque was 0. So this is in general for any position. Okay, and theta is the amount you've tipped away from vertical. So they do the calculations here, and if theta is 30 degrees, you get this torque about your shoulder as being 51 Newton meters. And they also do, now you can put any angle you want there, and so you could get what the torque is for the full range of motion from theta. So straight over your head, theta is 0, and then go all the way down until you've lowered that weight, so it's sitting beside your hips now, and this would be theta equals 90 degrees. If you graph that, you go from 0, it's a sine function, it goes up like that. This is 90 degrees. That's a huge torque. I mean, it's pretty hard to hold that there. And so, like I say, I don't know what exercise anyone would be doing lying on their back, holding that there. But anyway, this is the torque. Okay, so that's a good example. Let's see, oh yeah, the next one is the hip prosthesis. It's a little bit of a funny example. They're asking you for multiple torques depending on how the force in the hip joint is acting. I don't think I need to do that example. You could go through and look at that. It's just very similar to these. So I think that's good for now.